Okay, hopefully this is the last set of notes for this particular, or the last video for this set of notes. We got done last time by saying the total voltage drop in a circuit is equal in magnitude to the voltage gain inside a battery. This is an example of conservation of energy. So what this means is if we have a circuit, let's say it's a 6-volt battery, and that's how we label things. We just kind of write the voltage or whatever just to the side. Let's say that it's in this very simple circuit. There's our resistor. I'm not going to label the resistance with the resistor this time. If we have what's known as a 6-volt battery, and you've heard of different types of batteries, you've heard of 9 volts or 1.5-volt batteries. A 6-volt battery means that the gain in potential between terminals, between the two ends of the battery, is 6 volts. What this also implies is that there must be a 6-volt drop in the circuit in total to cause this. And where does this typically happen? Well, it happens at the resistor. So we're going to go back to the simulation now. So last time on the simulation, we had a short circuit. Let's get rid of our short circuit, okay? We don't want that to be a short circuit anymore. So I'm going to stop it. I'm going to change this by, let's see, we're going to put a resistor in. Okay, and let's spread this out a little bit so we can see. And now we see that we have a functional circuit. I'm going to go to conventional current just so it's a little bit easier, okay? If I turn values on, that'll be interesting. We have here a 9-volt battery and a 10-ohm resistor. Okay, let's remember those numbers. So we want to actually take a look at a couple different things that I've said so far. All right, so we showed that the, okay, let's do this. We're going to set up a voltmeter. Remember what a voltmeter does is it tells us the potential difference on either side of some circuit element. So I'm going to connect the two little probes on either side of this resistor, and look at that, I get a 9-volt drop. And interestingly enough, that 9-volt drop is the same as the voltage of the battery. Matter of fact, if I take this and put it over here, so I'm like measuring around the battery, that still says 9 volts. If I were to change the voltage of the battery, let's say I change it to, I don't know, 56 volts, essentially what I've done is now this has more voltage. It's kind of like each charge now has more energy that it's carrying. Look at that, the voltage changes again. So the voltage gain of the battery, that's a voltage gain, the charges are gaining energy, is equal to the voltage loss through the resistor. Now, what if I have more than one resistor? And this is getting a little bit complex right now. Let's say I have more than one resistor. Voltage gain in the battery is still 56 volts. I have a 28-volt drop there, and a 28-volt drop there. 28 plus 28 is 56. So the voltage gain of the battery equals the voltage drop for the entire circuit. Even if I were to change the resistance here, let's change this to 20, I should still find the same thing. 18.67, 37.33. Some quick math in my head tells me that that adds to 56. Okay, so the voltage gain inside a battery is equal to the voltage drop elsewhere in the circuit. All right, so a couple more things. Let's see, resistance and current. Let's take a look at that. So current is measured by an ammeter, and I have two tools to measure ammeters here. I have this, I also have this, okay? This is really how an ammeter works. This is just kind of a fake tool to make this a little bit easier. This doesn't actually happen in real life. You can't just hover over something and see what the current is, at least nothing I've ever seen. This says the current is 1.87. In order to get the actual current reading with a real ammeter, what I would have to do is break the circuit and insert the ammeter, and then see it says the exact same thing, okay? I can even change the voltage up and down, and those two current readings will always stay the same. So let's go back to 56. Okay, so one thing I want you to notice is, let's move the fake ammeter away. Ammeter, maybe? I don't know. Ammeters and voltmeters get connected differently. Ammeters go directly into the circuit. You have to wire them directly in. Voltmeters, you just kind of take the two probes and you touch different, and you can kind of work with them outside the circuit. It creates an alternate pathway. So that's something I want you to notice because that's very important. Let's see what else here. Okay. Let's take a look at this 20 ohm resistor. Let me actually put another wire in here so that's a little easier to measure. Take a look at this 20 ohm resistor. I'm just going to move this around a little bit so it's easier for us to measure. Ooh, what's this? We don't need this. There we go. Okay, there we go. We had an extra wire in there we don't need. Let's take a look at this. We know from the notes that R is supposed to be equal to V over I. So if R is equal to V over I, then that 20 ohm resistor should be equal to the voltage drop around it, 37.33, and the current going through it. Now, I could hover this right over. This is a specific type of circuit in which the current is the same everywhere. So I have 1.87 for the current through the resistor, same thing that this is reading us up here, and the voltage is 37.33. Let's see if that works. 37.33 volts divided by 1.87 equals just approximately 20 ohms. So it seems like our equation works. Matter of fact, if I go down over here and find the voltage across just this resistor, that's what you say, by the way, voltage across something, 18.67, you essentially have 18.7 divided by 1.87, that should give me 10. Notice that when I use the voltmeter, I do have to be very careful about where the probes are connected. Right now, they're just around this resistor. And what I mean by around is it kind of like the probes kind of let it bypass. Okay, they go around it. Watch what happens if I go around both. Now I have a bigger voltage difference because I'm treating this as just one object essentially. So you always have to be very careful to put the probes, these little things right here, around just what you're trying to find the voltage drop for. Okay, it has to be very specific like that. Let's see what else I can show you here. One thing you'll notice is I said that as they go through resistors, energy is being released. You might say, but the arrows are moving the exact same rate the entire time. Yes, that's true. Energy in this case means electric potential energy. They're not moving any faster or slower. So it's not really like cars in a bottleneck, but the analogy kind of works, but doesn't completely work. Let's see, I can show you the symbol version. Remember, these little lines here are the resistor symbols, and this is the battery. Actually, this is a cell symbol, but they're saying it's a battery. I like going back to this. We won't deal with battery resistance. We will actually talk about wire resistivity. I'm trying to think if there's anything else I want to show you quick. Oh, let me put a lamp in here. Lamps are kind of fun to play with. So let's get rid of that. Let's put and their lamp is just a light bulb, okay? Ah, look at that. Look at that light bulb. We can change how bright the light bulb is. Let's put it up to 50 ohms. Okay. So we can actually change how bright the light bulb is, but we'll talk about that later on. If I decrease the voltage too, that will change things. Very interesting, all this circuit stuff. Okay, let's see here. Yeah, okay, I'm going to get rid of the lamp. We'll play around with that more, and I'm going to put the resistor back in. And this is going to be a 10 ohm, or no, 20 ohm resistor, just like we had last time. Okay, and we're going to put this back up to 56 for no reason other than let's keep it consistent. Okay. Hopefully I've actually been showing you guys the right stuff here. I hope my camera work has been okay. All right. What we're going to do now, I think I've showed you everything I want. If there's any questions that you have, please ask me on Remind, and maybe I'll make a note to put them in the next video, or video chat me, or whatever. Just please let me know if there's any questions, okay? Because we are actually I'm gonna have you guys play around with this. You'll notice I gave you a couple of labs. We're actually going to try to do some labs on this, since we can't do them in person, and I'll explain those later on, okay? So I'm going to put this back. We're going to go back to the notes. And the very last section of notes talks about wire resistivity. Okay, Wires, conductors, even though they're conductors, they allow charges to move very easily. They do actually have very low but measurable resistances. And you can calculate the resistance of a wire using the following formula. Formula is right here. R equals, that's not a P, it's a rho. It's a Greek letter rho, okay? So it looks kind of like a P. What I usually do is I just kind of curl the tail of the P in. Rho times L over A. R is the resistance of a wire. So when you see this equation, you got to know it's the wire resistivity. Rho is something called resistivity. So you got to be careful. We have resistance and resistivity. I'm going to explain the difference later. L is the length of the conductor, length of the wire. A is the cross-sectional area. So as far as A and L go, the little picture down here helps you to kind of visualize it. You have A, the cross-sectional area is like if you slice the wire in half and then look at the slice that you made, that's the area, that's the cross-sectional area. Length is fairly self-explanatory. So our equation is R equals rho, see how I made that, L over A. And let me define what all of these are. Rho is resistivity. And what that basically means is how good of a conductor it is. A high resistivity is not a good conductor. Low resistivity, good conductor. You can think of it as how easily it lets charges flow. Low means big flow. Property of different metals. And you'll notice that the table right here says resistivities at 20 degrees Celsius. The 20 degrees Celsius is actually very important. This tells you the rho at 20 degrees Celsius for different materials: aluminum, copper, gold, nichrome, silver, tungsten. Resistivity is given in units of ohms times meters. You can tell these numbers are very, very low. One of them, however, is much bigger than the others. Nichrome is much bigger than the others. The other ones are very low. So why do we use copper wiring? Because copper has a very low resistivity, allows charges to flow very fast. You'll notice silver is actually lower, but I bet you can guess why we use copper instead of silver. Copper is a lot more abundant, okay? It's easier to get copper than it is silver, and you're only getting a marginally better resistivity for wires. So rho is the resistivity of different metals. It changes based on the metal. L is the length. A is the cross-sectional area of wire. Oh, and we're going to add to resistivity that the table in the reference tables is where you go for resistivity. And I do want to make one note about this. We're going to put a little star. We're going to write the resistance increases if temperature increases. That's very, very important because that gets asked every once in a while. I've just kind of given you this equation, just kind of threw it out at you. We're going to talk about why this makes sense, okay? So why it makes sense. Well, let's think about it. If you have a longer wire, remember resistance for a wire, essentially what you're looking for is how, what you're really looking for with resistance, it kind of gives you an idea of how much energy will be given off, will be dissipated for a certain part of a circuit. Remember, this equation is V over I. So if a resistance is bigger, that means there's going to be a greater potential difference, and therefore more energy will be used up. So why would a longer wire give off more energy or give up more energy? Well, think about it. What's traveling down the wire is the charges. If the charges are going down the wire and they have to work to get through the wire, the longer the wire, the more they have to work. So more energy is needed to get the charges through. And if more energy is needed to get the charges through, that means the resistance is higher and more work has to be done. So bigger L means bigger R. And we can actually see that on our diagram or on our simulation. What we're going to do is we're going to, where's my mouse? There it is. We're going to take the voltage, put it up here, or we're going to measure the voltage. We're going to do it across this wire. Okay. And you'll notice that right now it says that there's 0 volts. Okay, the voltage drop is 0. And that's because I set the wire resistivity to be tiny. Watch what happens if I increase the wire resistivity. I'm actually getting a voltage drop just from the wire. Now, if the longer wire means a higher resistivity and therefore a bigger voltage drop, then by changing the position of these probes, I should be able to change how big the voltage drop is and therefore the resistivity of the wire. So I'm going to do this. Start down here. Longer wire means bigger voltage drop. And what that must mean is that the resistance is bigger as I look at a bigger section of wire. So that's why this makes sense. If the wire is longer, then the resistance of that wire is bigger, that section of wire I should say, and therefore if the resistance is bigger, the voltage drop is going to be bigger, assuming that we keep the current the same. The voltmeter doesn't affect the current, okay? That voltmeter is not affecting the current at all. Matter of fact, I could take this voltmeter off. It's still not affecting the current, still 1.21. However, if the current stays the same and the resistance gets bigger, the voltage drop must get bigger as well. Okay, I'm going to stop there. We're going to talk about the other ones in a little tiny video in just a minute.